Hi, my name is Peter Hansen. I'm a professor of economics at the University of North Carolina in Chapel Hill. And I've been working with econometrics, things related to statistics, for many years, too many years. But I wanted to go through an analysis of some recent COVID-19 data that I have been looking into, specifically in relation to the new British variant, the B.1.1.7 variant of the SARS-CoV-2 virus that seems to be spreading much faster than the older variant. And so I'll just show you why we know, how can we know that? How can we be so sure that the new variant is spreading much faster? So what you see here is a web interface, a Jupyter interface, where I'm going to run some Julia code, which is a way to analyze data. If you know MATLAB, it can do these kind of things, Python. So here are the data. And where did I get the data? Well, I got those here from Statens Serum Institute. This is an institute in Denmark that collects these data and shares them. And one can log in and see how the numbers have been developing by week. So you had how many new confirmed cases per week. They use week numbers. Right now, we're at the end of week 6. So the last updated data were in week 5. There were 3,084 cases. And they tried to sequence this many. They successfully found the genome in this many tests. And that's a lot of them. They're really sequencing a lot of the positive tests here in 2021. And this is the number of B.1.1 variant. And you can see how the proportion of B.1.1 variant has been increasing. So those numbers I just copied in here, and they're up in the table here, the week numbers, the cases, the number that was successfully sequenced, and the number of cases that were B.1.1.7. These are just some old data that I'll be using later to check if things work. This was like what I collected a week ago and 2 weeks ago. So we can see these ratios. We can compute them, and we can compute the standard errors on those. Now I forgot to run this code here, so I need to run this again here. So now it's gonna create this data frame in Julia, and which looks like this. And here it computes the ratios and the percentages that you already saw that the Statens Serum Institute had computed. So these ratios come down here up to 30.9% in the most recent data set from last week. And here's some standard errors in those that just follow the standard formulas for binomial data. So we can look at what the prevalence then is of data. We can try and plot that, plot these percentages along with the standard errors. And the first time you run Julia, it takes a little while to show the first figure, but this is what it looks like. So by week, we have seen how the percentages have been increasing week by week, so we're just over 30% now. Now we can try and analyze these data and try and figure out how much faster does the new variant grow. So if A is like the old virus and B is the new so-called British variant, then they grow from week to week by a scalar that is either AT and BT. And what we're going to assume is that these two scalars are proportional to one another. There's basically the new variant is more infectious than the old variant by a scalar that is gamma, and by more infectious implies that gamma would be larger than 1. So now the task is to estimate gamma. So how much faster is it going? And we can look at, we have some very simple ways to look at that, because if it's growing by a rate that is gamma faster, well, then we can look at the increase in the B.1.1 variants and divide it by the increase in other variants. And for that, we can use the sequence data. So now we don't see these because by A and B here, I mean sort of the total number out there in the population. And we only collect some of these data. Not everyone is probably caught by a positive test. And also not all of them are sequenced, but we're going to assume that these sequenced data are representative of the ones, general population, and we know that they are representative of the positive tests that are collected, because the vast majority of those are found just by random sampling. And now that they sequence almost all of them, they will of course catch that. So here's what that's going to look like if you want to calculate these numbers. Well, before I should just say it, so here you can sort of infer what the numbers have been growing by using the percentages of positive tests, because they didn't sequence all of them. And so now we're going to use this trick where we look at the increment in B11 variant divided by the increment in non-B11 variants. And these are what the numbers look like. And so it'd be nice to add some standard errors to these. You can see these weekly crude estimates of gamma has been jumping around 1.5 and 2, with some variance. And there's a way to sort of compute how much uncertainty there is here. Now you learn this in a first year graduate course in econometrics in at least in the US graduate programs, you will learn about delta methods and other things. And so we can look at what that would look like when we add these error bands here that accounts for the correlation that is across these measurement points. So it looks like this. So it looks like gamma is somewhere between 1.5 and 2, and in fact the number is 1.759. But this is not necessarily the best way to compute this. We can actually extract more information. There's a better way to extract information from the data by using maximum likelihood. And to do that, to set it up, I'm going to add a trend line, and I subtract 5 so it aligns with the week numbers. Now, so lambda here is going to be the fraction of positive test, that is the B11 variant. And we can, so this is how it's defined. Then by the model we had before that said that the old variant increased by HC and the new variant by gamma times HC, we can actually conclude, or we can infer, what the next proportion is going to be the week after. So it's just going to follow this very simple dynamics. And what does that look like here? Well, once we write it out from small number to 1, it's going to grow this fast. And it's actually a very simple model. It's roughly 1.8 or 1.75 was what we found before, but here I just plotted by 1.8. And here are the numbers that you saw in Denmark week by week. And I got a great suggestion from someone on Twitter to add some lines. So you can see this is how we're going to step up week by week. So right now we're here. We would expect to be up there next week. And 2 weeks from now, we're going to be close to 60% and so forth. And actually, this is where we are, because these data are a little old. These are week 5. This is going to be where we are in week 6. And we are actually in the last day of week 7. So we are somewhere here, on Thursday next week, we'll probably be at 60%, because Thursday is the middle of the week. Okay, so knowing how this lambda evolves, we can actually write down what's called the log likelihood function, the likelihood function for the data. That the sequence data are thought of as a random sample. And so the probability that one sequenced test is B11 is going to be lambda t. It's going to be the probability of that. And if they're all IID data, so random sample from the general population there, or from the positive test, then what we will see is that the distribution of these tests would be binomial distributed. So the number of B11 is going to be xt, and c is the number that we successfully sequenced. They're going to follow this binomial distribution. This is the probability distribution for mass function, probability mass function for binomial. We take log, we have many sample periods. We put it all together, and from here we can try and estimate the unknown parameters, which is gamma, so the rate that B11 grows faster than the other one. And then this a starting point we need. So as was very nicely pointed out by a friend on Twitter here, Peter Dalgaard, when I sort of posted the first one, I'd done some maximum likelihood, he said, well, you know what, why don't you just do logistic regression? And by the way, this is what the code would look like if you use the right parameters. So you have to weight the data properly. So there's some weights, and you have to tell it's binomial, and then you can actually use logistic regression instead. And so I jumped on that. I've been using that ever since. So logistic regression is then formulating how this lambda t evolves over time. And it's actually better to do that in terms of what is called the odds ratio here. And because it has a much simpler dynamic, it basically just involves rho t is equal to gamma rho t minus 1. So it really goes much simpler forward. And from that, we can also, having seen that, we can write that in this way here with an exponential. So this is where the logistic model is sort of validated to be consistent with the model we had above, that it has this form here. And so the two unknown parameters in this model, so the way to reparameterize the model, is alpha and beta. And there is like a one-to-one mapping. So gamma is equal to the exponential of beta, and the starting sort of proportion or odds ratio is going to be exponential of alpha once we estimated this. Now I'm not going to use the R package. I'm going to use well, it's the same package. It's just been implemented in Julia as well, and roughly the same commands. Weights is like this, binomial like that. So we're going to run that, and that happens fairly quickly to estimate that. Again, the first time you call it, it takes a little longer in Julia because it's compiling things. So here came the estimates. This is alpha, this is beta, and just repeating those numbers for no particular reason here. Now we can now take the exponential value to beta and see what is our estimate of gamma. So it's 1.77. So not so far from the average we did with our very sort of crude estimates before of the weekly estimates. And we also sort of get the confidence intervals. So it's between 1.73 and 1.82 with 2 decimal points. Now this is at a weekly rate. So per week, it appears that B11 is growing at a rate that is by a factor that's 1.77 faster than the old variant. And we can translate that to a generation period, which I believe in Denmark they use 4.7 days. So I'm sticking with that. And in that regard, it's going to be 1.47 is going to be the number. And here we have the confidence interval as well. If you want to know what is per day, then it looks like the B117 virus is 8.5% more contagious than the old variants. So, well, how careful would we have to be? How much lockdown, how much precautionary measures, how extra careful would we have to be with hand washing and other things in order to contain this new variant? Well, we basically had to do something that would bring that would contain the old variant so much that the replication number would be this small, so less in between 0.67 and 0.69. So that's really showing how much more difficult it is to contain the new variant compared to the old one. Just showing how well the model works. So here you have the empirical ratios. The red line is the one that we estimated from the model. So you can see they line up very nicely, and there are many different ways of looking at that. This shows what we can expect going forward. So the model says that we are around 30.8% right now. Next week would be 44.1%. Then we're going to hit 58.3, 71.3. So you can see it's going very fast now, and very soon we'll be close to 90% of the cases. Now we can ask, when will the new variant become the dominant variant? And the model also tells us that because we just have to figure out when is this lambda t going to be equal to 50%. So we're going to solve for the time in here for which that happens. We rearrange some expressions. So the answer is it's going to be time 6.41. Now, time is here the week number, so it's going to be in between week 6 and week 7. Now, the midpoint in week 6 is a Thursday, so we have sort of work out what does 6.41 mean. Well, Sunday in week 6 is 3 days after Thursday. That would be 6.42. That means that today, which is Sunday in week 6, is actually the first day where the B.1.1 variant had the majority of new cases, sort of plus minus a couple of days perhaps. Now here's the scatter plot for showing what the model is predicting and where the numbers actually fell. And you can also see these line up very well. That's looking at the raw numbers. We can take log on both sides. And this also just shows how nicely the actual data here line up. And there are other data elsewhere that have estimated this rate and how much more contagious the B.1.1 is. And they sort of line up with the numbers we have for the Danish data. But because the Danish set is so complete and evidently so clean, have very few issues, there's just week 52 that is standing out a little bit, but that was the week of Christmas in Denmark. So maybe that is explaining why there was a slightly higher proportion that week for some reason. They weren't quite sampling right, or maybe they were contact tracing more that week. Anyway, so it looks like that. And odds ratios is just another way of looking at it. It looks very similar. And the linear scale, so this is alpha plus beta t. You can see how it lines up with the actually observed odds ratios and the uncertainty associated with that. Now, this plot here, I think, is just this is nice because this is showing the proportion of B.1.1 week by week. So here's what we saw. There's also showing what, maybe you can zoom in a little. We can see the shaded areas where the model is with the uncertainty that we have, because there's still a little bit of uncertainty about gamma. Now, is it 1.77 or is it 1.82 or 1.575? Well, the shaded area reveals that. So there's really not much going on in terms of the rate of B.1.1. It's very nicely nailed down. And going forward, it's going to predict this. No, so we're already here, but we don't have data yet on week 6. But it's going to predict these numbers here with this band here. So you can see there's very little uncertainty going forward. This is just a graph that repeating things you already seen. So how fast are the cases for the new variant actually increasing? Well, there's a very nice formula here that tells you that. So if you know what the replication number is for all cases, so maybe you can look at the increase in cases or 5 days, so that's roughly a generation. That will give you an idea of what R is. Well, there's simple formulas here that you can then use to infer what the replication rate is for the new variant. You just have to know what the ratio is, and because we know gamma, and we know what that translates to in terms of how much bigger the replication rate is for B.1.1 over a week. So I just put in this number, which is within the confidence interval of a weekly rate. It's in the lower end. So it tells us that B.1.1 is growing by this much. You just have to scale it up by 1.45 and then subtract 0.45 times lambda, where lambda is the proportion of B.1.1 cases here and now in the last week. So we can do a crude estimate of what it is in replication number, because we saw what cases were growing by from last week to this week, or the 2 last weeks we had. And so here we have converting it from a 7-day week to a generation period of 4.7 days. So we get that this is total cases are changing from week to week by a factor of 90%. And then we can map that to, we can plug in what the proportion of B.1.1 cases is according to the model. Well, it's this number here. And then we can now translate the R value for all cases to the replication value for B.1.1 using the formula. And when we do that, we get that the latest number is 1.18. So that was in week 5. We'll have a guess at what it is a little bit later. So how much time does it take for B11 to double if this is the number? Well, you can plug that into the formula as well. And what you get is that it appears that B11 right now is doubling in Denmark every 20 days. So in 40 days, that's going to be 4 times as many cases and then 8 times as many cases, if nothing else changes. And of course, things will change. And so I've come up with this very cool graph to sort of illustrate what the R value for B11 looks like relative to what the proportion is. And I think I saved that over here in a figure. Let's see this one here. It's easy to see here. So you can see here, this is the proportion of all cases that are B11. This is what the replication number is for all cases. And from that, you can then compute. There's a function that tells you what is the replication number for B11. And I then also added, so if you're on this line here, you have 1 for the B11. If you're here, you have 1.1, 1.2, 1.3. And here are the Danish numbers, just using the weekly statistics. What was the replication number, just using the weekly growth in cases, not adjusting for how many tests were conducted or anything. So they're crude numbers. And then the proportion of B11 in the data. So here we saw the end of 2020, we were here, and now we've been zigzagging a little bit. And so for this week, we are at this 1.18. And I just looked at the most recent data in Denmark. So again, we can look at this. There's this database here that collects all the Danish data. And if I click here, it should sort of, you can go in and see what happened day by day, but how many cases there were on the day they were actually tested. And from that, I sort of can infer that we are probably on track to having around 2850 data, no new cases in week 6. It might be 100 less, 100 more. But if that's the case, then where we're going to land is going to be here, because we know where we're going to be in terms of proportion. We're going to be at these 44%, and then we can work out how much the total cases are changing, translated to a replication number. And so this is where we're on track to be. So cases seem to be sort of growing at this 1.18 still. So that's not good, but maybe not terrifying if you have a low starting point, which is where Denmark actually is. So now we can see what that means. So I've computed these. Let's see if that works. So just plugging in that rate, then using the weekly numbers, the old variant is going to die out gradually. And this is what the graph looks like for the new cases. It's increasing like this. And total cases is going to look like that. So, we're going to have a decline in cases in week 6. And if nothing else changes, then, the case in week 7 will be about the same as in week 6. And then they will start to increasing again, unless something changes, restrictions are tightened, people are more careful because they know this is going to happen, and so forth. Now let's try and look at a different country. Let's try and look at the USS. And I've recently found a paper. I should have put up the link for that, but there's a paper by someone who is at UCSD. That's where I got my I think it's a Scripps Institute at UCSD, Anderson. That's where I got my PhD a long time ago in the 90s. And I got in economics. And so he and many other people have estimated what the proportion of cases are in the US. And it's like 2% in the US by the end of January. So here 2 weeks later, we should be at 6%. So you can then use the function I created to calculate what is the replication number for or how much is the B11 growing by in the US right now. And so what you can go and do, you can look at the case numbers in the US, and it's probably a good idea to use this moving average, so 7-day moving average. So you can do this, and you can then go 7 days back, and then you can look at increment. So that you can use to plug in what the rate of growth of change is in all cases, and then assuming that B11 is also 1.77 more contagious in the US, as it was found to be in Denmark and in other countries, then it appears that the B11 cases are growing by a factor of 1.34 in the US right now. And if you want a replication number in the US, then it comes out to 1.225 right now. I don't know why I'm repeating that here. I guess I should have write US here. So here we can look at what cases is going to look like. So the old variant is dying out fast. These are around 100,000 cases in the US right now, and so that's going to continue to go down. There are very few cases in the US, so we won't really see B11 for quite some time. Maybe it will become the dominant strain in week 10 or 11, and then we'll see cases grow again. Now, this is of course not factoring in all the good things that are happening. More people being vaccinated. Maybe people are going to be more careful and other things. In any case, we will probably not see this very rapid increase because more people will be protected from the vaccines. Now we can also look at Florida, because in this paper by Anderson and co-authors, they found that number to be, I think it was 4.5% in the end of January. So that will, using the formulas for how lambda involves, we know it will be around 12.9% 2 weeks later, so now. And then we can look at the cases, how cases have increased in Florida, and what the rate of change has been. So they've also been declining there. And so this is looking a little bit worse in Florida, perhaps. They are still going to see declining cases. So 10,000 is the number here. But because they're further along, they have a higher fraction of B11 cases. It will quicker become the dominant strain already in week 9 and 10. And after that, they would see rapid growth in total cases because B11 is just growing faster than the old variant. Again, vaccination is hopefully going to put a big damper on this. So that's what I had to say about the analysis of the data, why we know that the new variant is so much more contagious relative to the old one. We can almost eyeball it from these very crude estimates week by week, and the formal analysis come out with the same number, 1.77. And then there are some tricks by which we can work out what the replication number is for the B11 just from the total cases. And an advantage of that is that it takes a long time to actually sequence the data. So look, the B11 number we get with a big lag, whereas getting the replication number for total cases is something we can do much faster or much more, here and now. And having this formula then gives us a way to get the B11 replication number much quicker. We don't have to wait for the data, for the sequence data to come in. And so we get a finger on the pulse. We know what's going on here and now. So that's what I had to say. Thank you for listening. Hopefully it wasn't too long. And happy Valentine's, everybody.